It's a sunny but cold day in Cambridge today. It was cold and foggy yesterday. And 200 million years ago, it was... Well, hang on, there's no way of knowing that, surely. Well, perhaps there is. Researchers at the University of Cambridge may have uncovered a way to determine ancient climatic conditions by examining sediment rings in million-year-old seashells. I met up with Professor Simon Redfern, who worked on the project, and first asked him why we would want to know the climate from so long ago.
People are very interested to understand current changes in global climate and global temperature. And to understand and put those in context, you need to know what has happened in the past. The best information that we can get is by looking in more recent past at things like tree rings and actually even growth of shells in estuaries today, which record in their structures past climate, past temperature variations and seasonal variations. But if you want to go back further, then you would go to ice cores. People are extracting ice cores in both the Arctic and the Antarctic. And the oldest ice core material that you can obtain is from the Antarctic. That's about 800,000 years old. But if you want to go back even further into past Earth history, so the Earth is 4.5 billion years old, and we can scratch at that sort of historical timeline by looking back in these sediments. The geochemistry, the chemistry of organisms and minerals that occur in the fossil record effectively give us a clue as to what the temperature variations were and the climate variations going back hundreds of millions of years.
Can you tell the exact temperature, or are we looking at general trends here?
The method that is used by paleoceanographers, these are people who try and look at past climate and past ocean temperatures. They have managed to robustly determine the ratios of particular elements within a shell and correlate those with the temperature of the ocean. So we know pretty accurately now, if you measure an amount of magnesium, for example, in these calcium carbonate shells, what that magnesium concentration means. What has not been clear is why this works. So why is it that the magnesium incorporation into the shell gives us a temperature variation? And is the magnesium even incorporated into the shell, or is it trapped in other parts of the shell structure? So is it a part of the protein membrane, for example? What we've done is we've looked at the nanometer length scale at how these chemical variations are occurring. And what we observe is that the magnesium isn't homogeneous throughout the structure. It varies, and it varies cyclically. The magnesium is really incorporated into the mineral crystal structure. It replaces calcium, and that gives confidence in the method, actually. Really, we are looking at these chemical variations in shell chemistry that correspond directly with the temperature of growth of the shell.
So rather in the way that looking at the rings of a tree would be more useful than taking the whole tree and mushing it all up and seeing what overall it has inside it, you are looking at the rings in the plankton rather than just destroying them and looking at the whole composition.
Yeah, that's correct. Although the variations in magnesium day-night are not directly related to the temperature variation day-night, what they can tell us in particularly slow-growing plankton that may live over a year or more is seasonal variations. So you get an idea of whether there are extreme climate events, for example, within the growth period of the shell.
So how easy is it to get a sample of this? Is it an easier method than going to Antarctica and digging up an ice core?
Obtaining the plankton shells does require coring into the ocean, and actually that's probably more expensive than going and looking at ice cores, but you're looking at a different timescale, so you have no choice. This is the only way to get back beyond a million years or so. And there's an international program of drilling into the ocean floor. And the great thing about these plankton shells that we're looking at is that they're preserved within the sediment, so you can identify them. You can look under the microscope, you can pick out all the little foram shells that you find. What we've done looking at the shell structure itself is then looked at even more smaller scale. And to do that, we take a shell and do a process called focused ion beam extraction, where you use a little beam of particles to mill out a tiny fragment of shell. And then this tiny fragment of shell we've measured in a synchrotron light source. So a synchrotron light source is an electron accelerator. It generates very, very high intensity X-rays. You can focus down onto the shell at a sort of 20 nanometer length scale. And there are only a few places in the world that have got these sorts of X-ray microscopes. We've had to go all the way over to California, actually, to do the experiments.
That's no hardship.
When you're working at the synchrotron, you work there 24 hours a day because the experiment costs a lot of money, so they like to use their time effectively. But it's a very beautiful location, actually. It's the Berkeley Advanced Light Source, which sits in the East Bay across from San Francisco. And the synchrotron itself is the most splendid location. You get a view out across Golden Gate on a clear day into the Pacific, and it's a beautiful place.
So just lastly, what next? Where are you going to take this work?
So up to this point, we've looked at magnesium, which is known to be the main proxy for temperature in oceans from these plankton shells. And the next thing is to try and look at other elements that are important in metabolism within an organism. The plankton shells are one aspect, but then there are other organisms, other biominerals that are also important to understand. So these include things like corals. So how do corals change their chemistry as the ocean chemistry changes? And that's important today in understanding, for example, coral bleaching and the viability of corals, not just in coral reefs, but also cold water corals that we have around us in Great Britain.